In the fall of 1962, something unbelievable rolled into American showrooms. It didn't have a giant engine, it didn't rely on brute force, and it didn't wear racing stripes to get attention. Instead, it carried a small aluminum V8 with a strange snail-shaped device bolted to the exhaust. Most buyers had never seen anything like it. Even many mechanics didn't understand it. But what almost nobody knew was that this little Oldsmobile was about to introduce a technology that would dominate the automotive world decades later. Today, nearly every performance car seems to have a turbocharger. From everyday pickup trucks to European supercars, forced induction is everywhere. Walk through any modern dealership and you'll find turbos on everything from family sedans to luxury SUVs. It's become so common that manufacturers barely mention it in their advertising. But back in 1962, the idea sounded almost ridiculous. Americans believed there was only one way to make power: build a bigger engine, add more cylinders, increase displacement. Simple. Oldsmobile had a completely different idea, and what happened next changed everything. Most people remember the muscle car era as a battle of massive V8s, the 409S, the 427S, the legendary Hemis that shook the pavement. But hidden beneath that history is one of Detroit's boldest engineering experiments. An experiment so advanced that customers weren't ready for it, dealers couldn't explain it, and even the company's own service department struggled to keep it alive. You think you know turbocharging. Not like this. The early 1960s were a strange time in America. The space race was accelerating. NASA engineers were pushing technology further than ever before. Jet aircraft captured the public imagination. Supersonic flight wasn't science fiction anymore, it was reality. Companies wanted their products to sound futuristic. Jet became the magic word. Jet engines, jet age styling, jet-powered dreams. Television commercials showed cars alongside fighter planes. Magazine advertisements promised rocket-like acceleration. Marketing departments went wild with space-age terminology. Meanwhile, Detroit faced a growing problem. Bigger engines meant more weight, more fuel consumption, higher production costs. Insurance companies were starting to notice performance cars. Emissions regulations lurked on the horizon, though few executives took them seriously yet. Chevrolet was preparing the Corvette Stingray with independent rear suspension and sleek new styling. Ford had high-performance Fairlanes in development. Pontiac was experimenting with cars that would soon evolve into the legendary GTO. Horsepower wars were beginning. Oldsmobile engineers asked a dangerous question. What if they could build a smaller engine that performed like a much larger one? That idea landed on the desk of engineer Gilbert Burrell and his team. Instead of designing another huge V8, they started with Oldsmobile's lightweight aluminum 215 cubic inch engine, the same basic block that would eventually power British sports cars for decades. The block itself weighed only about 320 pounds thanks to its aluminum construction, a material still relatively exotic in American automotive manufacturing. With a 3.50-inch bore and a 2.80-inch stroke, displacement measured just 215 cubic inches or 3.5 liters, tiny by American standards, laughably small compared to what competitors were building. But there was a catch. A small engine couldn't compete with larger V8s unless someone figured out how to squeeze dramatically more air into it. Naturally aspirated engines breathe at atmospheric pressure. They're limited by how efficiently the pistons can draw air through the intake valves. Physics creates a ceiling. That's where the turbocharger entered the story. At the time, turbochargers weren't completely unknown. They had been used on aircraft during World War II to maintain engine power at high altitude, where thinner air starved conventional engines. Heavy-duty diesel engines in industrial applications were beginning to adopt them as well. Caterpillar and Cummins saw the advantages in trucking, but putting one on a production gasoline passenger car, nobody had done it successfully. The challenges seemed insurmountable. Oldsmobile decided to become the first. The engineering team partnered with Garrett AI Research, a company with extensive experience in aerospace turbocharging. Together, they adapted aircraft technology for automotive use. The result was a compact turbocharger that could bolt directly to the exhaust manifold, spin at tremendous speeds, and force compressed air back into the intake system. But there was a problem. Actually, several problems. Turbochargers create heat. Lots of it. Compressing intake air dramatically raises combustion temperatures. Higher temperatures increase the risk of detonation, the uncontrolled explosion inside the cylinder that mechanics often describe as knocking or pinging. It sounds like marbles rattling in a coffee can. Severe detonation doesn't just reduce performance, it melts pistons, cracks ringlands, pounds bearings into scrap metal, destroys engines in minutes. At just over 5 pounds of boost, the Jetfire already lived dangerously. The engineering team needed an answer. Instead of lowering compression like modern turbo engines, they went the opposite direction. The Jetfire retained an astonishing 10.25 to -1 compression ratio. That's high even by naturally aspirated standards of the era. Most contemporary engines ran between 8.5, 1 and 9.5. Adding forced induction to such high compression seemed like automotive suicide. How could that possibly work? Their solutions sounded almost like science fiction. They created a special fluid injection system called turbo rocket fluid, packaged in distinctive glass bottles sold through Oldsmobile dealerships. It was a carefully measured mixture consisting primarily of distilled water and methyl alcohol, along with corrosion inhibitors to protect internal components. The system stored this fluid in a dedicated reservoir mounted under the hood. Whenever boost increased beyond a certain threshold, this fluid sprayed into the intake stream through precisely calibrated nozzles. The evaporating mixture cooled combustion temperatures instantly, suppressed knock, and allowed the engine to survive under boost. The concept was brilliant. It worked. At least in the laboratory. The little V8 suddenly produced 215 horsepower, exactly 1 horsepower per cubic inch. That number may not sound shocking today, but in 1962 it was extraordinary. Most American engines produced somewhere between 0.65 and 0.85 horsepower per cubic inch. Reaching 1-to-1 naturally aspirated was considered exceptional engineering. Torque climbed to around 300 pound-feet at just 3,200 revolutions per minute, rivaling much larger engines. Chevrolet's naturally aspirated 327 V8 produced similar horsepower, yet required significantly more displacement, more weight, and more fuel. Oldsmobile had achieved something Detroit thought impossible: power without proportional size, efficiency without sacrificing performance, and then the real test began. The Jetfire reached dealerships late in 1962, installed primarily in the sleek Oldsmobile Cutlass. From the outside, it looked relatively ordinary. No hood scoop announcing what lurked underneath. No wild graphics screaming about turbocharging. Just clean styling hiding revolutionary engineering. A small turbo rocket badge on the front fenders was the only hint. Salespeople struggled to explain what made it special. Road and Track magazine was stunned. Motor Trend praised the smoothness and effortless acceleration. Contemporary testing recorded 0 to 60 times around 8.5 seconds, while quarter-mile runs landed near 16 seconds at roughly 85 miles per hour. Those numbers placed it firmly among America's quicker compact cars, competing directly with vehicles carrying much larger engines. Drivers loved something else even more: mid-range acceleration. Unlike many naturally aspirated engines that needed high RPM to make power, the Jetfire surged forward as boost built. Passing on the highway required only a gentle press of the throttle. Boost arrived. Power followed. Traffic disappeared in the rearview mirror. One engineer reportedly joked, "It feels like another engine climbs under the hood halfway through the gear." Customers smiled during test drives. Checkbooks came out. Then ownership began, and everything became complicated. The turbo rocket fluid reservoir required regular refilling, roughly every 1,000 miles depending on driving habits. The tank held about a quart, ignore it, and the engine protected itself by limiting boost through a wastegate control system. Some owners misunderstood the warning light on the dashboard. Others didn't bother buying replacement fluid because it seemed like an unnecessary expense. A few simply poured ordinary water into the tank, figuring it was close enough. That was a disaster. Without the correct alcohol mixture, combustion temperatures rose rapidly under boost, knock increased, pistons suffered, spark plugs fouled, performance disappeared. What should have been a quick, responsive engine suddenly felt sluggish and rough. Customers complained. Dealers scrambled for solutions. Service departments weren't much better prepared. Many mechanics had spent decades tuning carburetors and distributors on conventional engines. They understood ignition timing curves. They knew carburetor jetting. They could diagnose valve problems by sound. Suddenly, they faced pressure switches, turbo plumbing, fluid injection systems, and unfamiliar calibration procedures. Training materials existed, but not every technician studied them carefully. Diagnosis became guesswork. One dealership mechanic later recalled that cars sometimes arrived with perfectly healthy engines, but technicians blamed the turbo for unrelated ignition issues because nobody truly understood the system. Spark plugs were replaced unnecessarily. Carburetors were rebuilt when nothing was wrong. The turbocharger became a convenient scapegoat. Customers grew frustrated. Repair bills mounted. General Motors grew nervous. Word of mouth turned negative. Potential buyers heard stories about complexity and maintenance headaches. Oldsmobile's revolutionary technology started looking like a liability instead of an advantage. But hidden beneath those service headaches was another engineering challenge: turbo lag. Modern enthusiasts understand lag as the delay between pressing the accelerator and feeling boost. In the early 1960s, turbocharger design was still primitive. The Garrett T5 turbo used on the Jetfire relied on exhaust energy to spool up, but bearing technology, turbine efficiency, and compressor aerodynamics hadn't yet reached modern standards. Shaft speeds needed to climb dramatically before the compressor moved enough air to create meaningful pressure. Below about 2,800 revolutions per minute, acceleration felt ordinary, just another small V8. Then suddenly, boost arrived. The surge surprised many first-time drivers. Power delivery wasn't linear like they expected. It built gradually, then rushed in all at once. The car hesitated, then lunged forward. Some loved it. Others found it unpredictable. Driving techniques needed adjustment. Experienced Jetfire owners learned to keep the engine spinning higher, anticipating when boost would arrive. They understood the power band, but casual drivers expecting conventional behavior were often caught off guard. Still, engineers continued refining the calibration. Wastegate settings were adjusted. Carburetor tuning improved. Ignition timing evolved. Each revision made the engine slightly more manageable, slightly more predictable, but public perception had already started turning. Then another unexpected rival appeared. Across town, Chevrolet launched the turbocharged Corvair Monza Spider. Unlike Oldsmobile, Chevrolet chose a different path. Instead of fluid injection, the air-cooled flat six used lower compression to reduce detonation risk. Compression dropped to 8.01, sacrificing some naturally aspirated performance to gain boost tolerance. It produced around 150 horsepower from 145 cubic inches. Impressive, but not as ambitious as the Jetfire. Both companies claimed groundbreaking technology. Marketing departments promoted jet-age engineering, but neither car sold in massive numbers. Why? Because America wasn't asking for efficiency through technology. America wanted cubic inches, raw displacement, tire-shredding torque, the rumble of big block exhaust, performance you could hear before you could see it. The GTO arrived with 389 cubic inches. Ford unleashed larger FE engines, displacing 390, 406, and eventually 427 cubic inches. Chrysler answered with massive wedge and Hemi V8s that didn't need forced induction to make power. Horsepower became associated with displacement, aggressive styling, and tire smoke. Simplicity sold. Complexity scared buyers. Turbocharging suddenly seemed unnecessarily complicated. Why mess with injection systems and special fluids when you could just bolt in more cubic inches? Oldsmobile's revolutionary little engine looked like yesterday's experiment almost overnight, and the financial reality became impossible to ignore. Development costs were high, production volumes remained low, service issues created warranty expenses. Dealers weren't enthusiastic about selling something they couldn't properly maintain. Production lasted barely 2 model years. Only about 9,600 Jetfires were built between 1962 and 1963, making them among the rarest production Oldsmobiles of the era. By 1964, the model was discontinued. Many dealerships actually removed the turbocharging hardware from customer cars under factory-approved service campaigns. Naturally aspirated components replaced the complex forced induction system because maintaining them proved easier and cheaper. A carburetor swap, different intake manifold, conventional ignition timing. Imagine that. Thousands of history-making turbo engines quietly disappeared, not because they lacked performance, not because the engineering was fundamentally flawed, because they were too advanced. The infrastructure didn't exist to support them. Mechanics weren't trained, customers weren't educated, the market wasn't ready. You can probably guess what happened next, but the truth is even crazier. The automotive world essentially abandoned gasoline turbocharging in America for years. The technology worked, but nobody wanted to deal with the complications. Displacement remained cheap, fuel was affordable, emissions regulations seemed like distant concerns. Then came emissions regulations. The Clean Air Act, tightening federal standards, and the fuel crises of the 1970s completely changed engine development priorities. Overnight, the rules changed. High-compression muscle engines disappeared almost overnight, strangled by emissions equipment and low-octane unleaded fuel. Manufacturers desperately searched for ways to recover lost power while meeting stricter efficiency requirements. Horsepower collapsed, performance cars became embarrassingly slow. Suddenly, Oldsmobile's forgotten experiment didn't seem so strange anymore. European manufacturers began investing heavily in turbocharging. Saab built its reputation around turbocharged reliability, proving the technology could work in everyday driving. Porsche transformed the 911 Turbo into an icon of performance and engineering excellence. BMW experimented with turbocharged inline-sixes. Buick shocked the performance world during the 1980s with the turbocharged Grand National and GNX, proving forced induction could dominate American performance while meeting emission standards. By then, technology had finally caught up. Electronic fuel injection replaced crude carburetors. NOx sensors detected detonation before damage occurred. Engine computers adjusted ignition timing hundreds of times every second. Intercoolers cooled compressed intake air far more effectively than engineers in 1962 could realistically package into a production car. Wastegates became electronically controlled. Boost could be modulated precisely. Everything Oldsmobile struggled to solve mechanically became routine with electronics. The same concept, the same goal, but with technology mature enough to make it reliable. Most people don't realize how many modern ideas appeared first inside the Jetfire. Engine downsizing, forced induction, boost management, detonation control, high specific output, water methanol injection, which disappeared for decades, has returned in some high-performance applications like BMW M models. Today, a 2-liter turbocharged 4-cylinder making 250 horsepower barely raises eyebrows. Some produce over 400 horsepower. Ford's EcoBoost engines power everything from Mustangs to F-150 trucks. GM's turbocharged pickups deliver V8 performance from 6 cylinders. BMW's inline-sixes, Mercedes-AMG performance cars, Audi's TFSI engines, and countless others all follow the same philosophy Oldsmobile attempted more than 60 years ago. Make a smaller engine act like a much bigger one. Extract maximum power from minimum displacement. The difference? Modern technology finally made that vision practical, reliable, maintainable. Collectors now see the Jetfire differently as well. Finding a complete, numbers-matching Jetfire with its original turbocharger, fluid reservoir, plumbing, and induction system has become increasingly difficult because so many cars lost their unique components decades ago. Most were converted to naturally aspirated engines long before anyone considered them historically significant. Properly restored examples command impressive prices precisely because they're no longer viewed as failures. They're viewed as pioneers, visionaries ahead of their time. Engineering museums and automotive historians frequently point to the Jetfire as the world's first mass-produced turbocharged passenger car. While later turbo vehicles achieved greater commercial success, Oldsmobile deserves credit for taking the first truly bold step, for risking resources on unproven technology, for believing small could compete with big. That courage matters. Innovation rarely looks perfect the first time, The Wright brothers didn't build a 747. Edison's first light bulbs lasted hours, not years. The first computers filled entire rooms. Every revolutionary technology goes through awkward stages. Sometimes the greatest breakthroughs don't fail because the idea is wrong. They fail because the world isn't ready. That's exactly what happened here. The Jetfire wasn't defeated by bad engineering. It was defeated by limited service knowledge, immature supporting technology, customer expectations, and a market that still believed bigger automatically meant better. It arrived during an era that valued simplicity and displacement over complexity and efficiency. 20 years later, turbocharging became the future. 40 years later, it became the industry standard. And today, it's almost impossible to imagine modern performance without it. Walk through any auto show, read any automotive magazine, watch any racing series. Forced induction dominates. Formula One engines are turbocharged. Rally cars are turbocharged. Sports cars, luxury sedans, pickup trucks, even economy cars wear turbochargers. The technology Oldsmobile pioneered is now everywhere. So when you hear the whistle of a turbocharger spooling up on a new sports car, remember this forgotten Oldsmobile. Remember the engineers who took a risk. Remember the 1962 Jetfire. Beneath its modest hood was a 215 cubic inch aluminum V8 and an idea so ambitious that history needed decades to catch up. That's what makes the Jetfire story so remarkable. It proved that intelligence could compete with displacement, that innovation sometimes arrives long before the market is prepared, and that being first doesn't always mean being successful. Sometimes it simply means showing everyone else where the road is going. Sometimes it means planting a seed that takes generations to fully grow. The Jetfire was a commercial failure, but a conceptual triumph, a market disappointment, but an engineering achievement, a forgotten car that predicted the future. If you enjoyed this story, let me know in the comments which forgotten engine you'd like to explore next. And make sure to subscribe, because there are plenty more incredible automotive stories hiding beneath the surface of history. Stories of bold ideas, failed experiments, and technologies that changed everything when the world finally caught up.